Hello, this is part 3 of types of solution sets. So we are in the process of finding solutions for this system of equations, and we know that these solutions are, the variables are of this type, where x2 and x5 are free variables. That's the information we gain from the RREF of the augmented matrix. But whenever there are dependent variables and free variables, that is the case in which the system has infinitely many solutions. And by evaluating the free variables as specific values, we are able to come up with specific solutions, to come up with one of multiple, one of infinitely many. Okay? And so that was the topic that we discussed last, where we decided to say, this value of a free variable x2 and this value of free variable x5, we're going to substitute that for specific values. So we said, we're going to set x2 to be 0, and we're going to set x5 to be 1, and if x2 is 0, right, then we're going to get a value for x1, and with those two values of the free variables fixed at 0 and 1, then x1, x2, and x4 take specific values. So for these specific values of x2 and x5, then we would obtain that the values of dependent variables are 3 for x1, 3 for x3, and 5 for x4. Okay? And so here, this vector 3, 0, 3, 5, 1, this is one of many solutions. And what you should do now is pause the video right here and substitute on the left side of this linear system of equations. Substitute the values of x1 of all the variables by these values, and verify that the left side becomes exactly that value on the right hand side. Look, as you are getting ready to do that on your own with your own pencil and paper, I'm going to take a look at the first equation. You're supposed to do this for all these equations, but let's take a look at the first equation. So where we have x1 minus x2. So I'm going to try to do this here. So x1, we have x1 is 3 minus x2, which is 0, minus 2 times x3, and x3 has a value of 3, plus x4, which has a value of 5, plus 11 times x5, which in this case is 1. So what we want to do is to verify what this is. So here we're obtaining 3 minus 6 plus 5 plus 11, right? And 3 minus 6 is minus 3, and minus 3 added to 16, that gives you this number. And that number is exactly the number you have on the right side of the first equation. So you can verify by plugging in these values in these equations that indeed you would obtain all those values on the right hand side. And that is because this is one specific element of that set that we call the solution set, which contains infinitely many solutions. And so that was one specific case. That was by setting the free variables to arbitrary values or specific values, 0 for x2, 1 for x5, and 1. Why those two values? Well, the fact that they are free means you can set them to any values, right? So what if these free variables are set to some other values? What would happen if instead of, you could have here, what if x2 is 0 and x5 is 0? Both of them are 0. Or forget that, what if both of them are equal to 1? So for each combination of values, remember, we're assuming they're complex numbers, so you can set 1 to a complex whatever, right? So for each specific values of x2 and x5, you're going to get a different vector, and that vector is a member of this set, and this set is extremely, it has a lot of members. So the system is considered consistent because it has at least one solution, and this illustrates the procedure for coming up with the solution set. And so this is the theorems that we have that we're reviewing now. This is how the mathematical theory allows us to rule certain scenarios. Consistency is that property of a linear system of housing at least one solution. If the equations cannot be satisfied, then the solution set would be empty. But here is a way of ruling the consistency. You have the augmented matrix of the linear system. It has an RREF here denoted by B, and R denotes the number of nonzero rows. The system is inconsistent if and only if there is a leading one in the last column of the RREF. Okay, and here's another result. Suppose that B is the RREF of the augmented matrix, and that R is again the number of leading ones, or number of rows, non-zero rows. Then if R equals n plus 1, where n plus 1 is the number of columns of the matrix, then the system is inconsistent. So these are two ways of applying theory, mathematical theory, to come up with a conclusion of this system has an empty. So when the system is inconsistent, whenever we say inconsistent, then this implies that the solution set is equal to the empty set. We write that, or we write S equals, and we write the braces, and we don't write anything inside of those braces. So that is the type of solution set a system would have whenever the system is inconsistent. And here is a little bit more of theory. A is the augmented matrix, B is the RREF, R, same number of leading ones or non-zero rows. Remember, n is the number of variables, so if R equals n, okay, if R is exactly equal to n, the system is consistent, and more precisely, it has one solution and one solution only. It has a unique solution. Okay. When R is strictly less than n, which was the case on those examples we have discussed in this lecture, then the system has infinitely many solutions. So these infinitely many solutions is that scenario in which we have the set B be non-empty and the set F, and then we have that partitioning of variables, dependent variables, free variables, and so on. That would be the case when we have a system that has infinite many solutions. So the solution set in that case will have to be expressed in set form with a specification of those variables that are dependent on free variables. Okay, and I'll let you read this other theorem, free variables of consistent systems. Take a couple of minutes here and read this carefully, and here towards the end we have a schematic of how some of these theorems are working. Consistency is going to be that system that has at least one solution. If it is inconsistent, solution set is empty. There's no solution. So when the system is consistent, you may have either one of two cases. One case means there is only one solution, and the other case is that there is infinite many solutions. That can only happen if the linear system of equations is consistent. And this is the last theorem we have here. So if a consistent system has m equations in n variables, then the number of variables, if the number of variables exceeds the number of equations, then the system has infinite many solutions. So this goes back to that representation of that matrix vector representation. So this is telling us that the matrix of coefficients, we represent that as a rectangle. This would be a case in which that rectangle has a number of columns that is much larger than the number of rows. Okay, so this would be the matrix. I don't know, we can call this matrix, I'm going to call that M, and this multiplies the vector of variables, and this is equal to vector of constants. So this could be something that reads M times X equals B. Okay, so here the number of variables equals the number of columns in the matrix of coefficients, and if that number of columns exceeds the number of rows, then this would be one of those cases in which the solution set is going to have infinitely many, and certainly this means that there are dependent and free variables. Okay, dependent variables and free